In this lesson, we'll be looking at how to predict the products in a double replacement reaction, and also how to determine whether the double replacement reaction will actually occur. In double replacement reactions, the reactants typically start out as aqueous solutions. The solubility rules allow us to predict the relative solubility of the products that would be formed from mixing these solutions together. If the combination does not result in an insoluble or molecular substance, the reaction does not occur as is shown in the second example in the image. So here we have ammonium carbonate, aqueous, potassium sulfate, aqueous, and when you do the double replacement reaction, you still end up with aqueous products. So that means that this is a no reaction. On the other hand, if you were to take silver nitrate, aqueous, sodium bromide, aqueous, and allow those to react, you'll get a precipitate of silver bromide and sodium nitrate. And we'll see that species that remain aqueous or aqueous products are called spectators. By the end of the lesson, you'll be able to use the solubility rule to predict products as well as write net ionic reaction equations. So first we have to kind of discuss what solubility is. In order for a substance to dissolve, the solvent has to be able to separate the solute particles from each other. So in the GIF, we have water molecules, the little red and white ones. They come down onto the surface of a salt crystal and surround it, create a little hydration sphere, and because they have interfered with the electrostatic interactions between the ions, they're able to pull it off into solution. As a result of this, the size of the crystal is gradually going to disappear or be reduced, and you will end up with just solvated ion species in solution. How soluble an ionic substance is depends upon the size and the charge of its ions. So solubility decreases, it gets harder to pull it apart. As the ions get smaller, so the electrostatic forces are getting stronger because those charges are closer together, or as the charge gets bigger. Same idea. All right, so solubility rules allow us to determine if a double replacement reaction actually occurs. So here we have a double replacement reaction. It's not balanced yet, so let's go ahead and balance that, between sodium chloride and magnesium nitrate. Now you can write stuff down on paper, but it doesn't necessarily mean that you actually have a reaction. So if you think about it, we started out, we had sodium chloride aqueous, so they got solvated ions. Afterwards, magnesium nitrate, or we also had magnesium nitrate, also solvated ions. We do the cation switch, and now we have aqueous sodium nitrate and aqueous magnesium chloride. There isn't anything that has changed its state. They're all still just solvated ions. So this is a no reaction because there's no particular change in state. If you think about the 5 indicators of chemical change, so energy released, these are all in water, so we're not going to have any flames. Gas evolution, we don't see any little G's, so we know we're not making any gas. We start out, it's clear and colorless, and even after you've supposedly formed these products, still clear and colorless. I'm just going to have to tell you there is no temperature change, and we also don't have any precipitate being formed. And where we know that is because there's nothing solid being formed. So let's think about another example. So here we have, balance it again, the reaction between sodium chloride and lead-2 nitrate. And so we spot that we have that a solid is being formed. So therefore that last one on the indicators has been satisfied. So yes, because a precipitate was formed. So the solubility rules, it's listed in the reference packet. Most of them most cases, all you really need is what's shown in the yellow box. The thing that people have trouble with is that, whether you're talking about something that stays aqueous or something that forms a precipitate. So if it has anything here in this yellow box, that means it's soluble. It does not form a precipitate. So these are the ones that are going to stay aqueous. And then we look at the other case, and so these are the ones that do form precipitates. And PPT is a handy-dandy abbreviation for precipitate. And you notice that there are things that have large charges on them, like carbonate, phosphate, hydroxides. They are fairly small. Or if you have sulfides, they have a high charge as well. The exceptions would be if you have anything combined with it. That's the stuff that's in this yellow box. All right, so let's look at the combinations. So we have zinc nitrate and sodium carbonate. And so I want to show you a technique we're going to be using. So it is, I kind of abbreviate this as outer, outer, inner, inner. So we're going to take the outermost part, which is zinc on the first compound. And remember, carbonate is a polyatomic ion, so it goes as a group. So there's our outer, outer. And then we're going to do inner, inner, so that's what's left over. So we have sodium and nitrate. So that gives us our two combinations. So now we have to figure out if we have a precipitate or not. So remember, one of the big ones that was in the solubility chart was that if it had nitrate or group 1, alkali metals, cations, then it is going to be soluble. It's going to stay aqueous. There we go. So that means this guy over here, it's got both of them, is going to be aqueous. Oh, and I should probably erase that because it's going to write over it. The other one does not have that situation. It's got zinc and carbonate. Those weren't anywhere in that yellow box. So that means that zinc carbonate is going to precipitate as a solid. So now we do the same thing for the next one. So we got sodium and carbonate. That's not going to precipitate because it has sodium in it. And ammonium and phosphate. And that's not going to precipitate because it has ammonium in it. So you can do the swap if you want, but it works out to be that that is a no reaction. And so using this little shorthand notation of where you combine them together and then cross out the parts that will not form precipitates is kind of a shorthand notation, so you don't have to write out quite as much stuff. And so you just write down NR for no reaction. And then we got barium chloride and sodium sulfate. So turn the pen back on. So we have our outer, outer. That's one pair. That is not one we're going to cross out. And then we got sodium and chloride. That one is going to stay aqueous because it's got sodium in it. So we do our swaps, and we see that we will have a precipitate of barium sulfate. So we have a new term. It was on the original picture, spectators. So the ions that remain in solution, they started out solvated and they just stayed that way. They're just watching what's going on. They're not precipitating, are called spectator ions. So in reaction 1, the spectators are going to be sodium and nitrate because they stayed aqueous. In reaction 2, all of the ions are going to be spectators because there was no reaction. That's why there is no reaction. They're just watching what's going on. And in reaction 3, the spectators are going to be the aqueous ones again, so sodium and chloride. So net ionic reaction equations. Spectators, we're not really interested in them, so we want to have a way to be very concise. Just have the part that's actually doing something. So a way of relating it to something you may have already experienced. You know that when you get a paycheck, you don't really want to look at the gross pay because then you're reminded of how much stuff gets taken out by the government. Instead, you want to look at the net pay because that's what you actually get to spend. So that's why we do net ionic reaction equations. So here we have our zinc nitrate and sodium carbonate reaction. So there's a couple of different ways to do this. So one way, and this is how I initially tried to teach this, you identify the insoluble product, the precipitate. You write that down. It's still a product, so it still has to go over on the right-hand side. And then you point an arrow at it because it is a product. So it has to be on the right-hand side of the arrow. And then you just take it apart. The only way you can make zinc carbonate is by combining zinc ions with carbonate ions. And then you add states of matter to make it absolutely perfect. Make sure it's balanced. One zinc, one carbonate, one carbonate. It is. And so, yeah, pat yourself on the back. You've just balanced the net ionic reaction equation. There is another way to do it, and this is the way the textbooks tend to do it. They want you to write out a complete ionic reaction equation, and that's where you split all of these aqueous species into their separate ions. So we would have zinc plus 2, and then 2 nitrates, and then 2 sodium ions, and 1 carbonate, and then you do the same thing on the other side, and then you cross off the ones that are the same on opposite sides of the arrow. This is just a much shorter way of doing it, and that's the way I usually don't ask for complete ionic reaction equations. All right, so in the lab that we're going to be doing that goes with this lesson, we're going to be mixing a whole bunch of different solutions together and then looking at whether they form a precipitate or not. And the way you can tell if you have a precipitate, because we're working with microscale, is if you can't see through the drop, that means you have a solid present because you can't see through solids. And so you're going to get a whole bunch of things like, for example, and I'm sorry about the quality of this picture. It's not very good. I need a better camera. And so you see we got a bunch that are just clear. You can see all the way through it. That's the reason why there's a white part to the box and a black part to the box. This one didn't do anything. But you can see there are some combinations where we definitely get a solid. You can't see all the way through it. So I'm just going to do a couple of the combinations. So when you combine iron 3 chloride with sodium carbonate, you get a orange precipitate of some sort. And so the way we can change to pen, figure out what our net ionic reaction equation is figure out your pairs. So we got iron and carbonate. That's not soluble. Sodium and chloride, that is soluble, so we're not going to ignore that. We're going to totally ignore it. So or ignore the arrow. I should have gotten rid of that. So we have iron with a +3 charge, and I found it helps students if they can just write it down exactly the way it shows up in the initial combination equation. So we have iron +3, make it perfect, put an aqueous on it, plus carbonate -2, and that's also aqueous, and I did not leave myself enough space. And then you do the swap and drop. It is not charge balanced, so you end up with Fe2 and then CO3 3 times, and that's our solid. You still have to balance it, so we have 2 irons, so we need to put a 2 in front of the Fe+3 on the reactant side, and we have 3 carbonates, so we need a 3 in front of the carbonate anion on the reactant side. So that would be the net ionic reaction equation for the first combination that I have on here. And I forgot to put this on there, so outer, outer, inner, inner. So let's do another example. So if you combine copper sulfate with sodium hydroxide, you get this real pretty blue gel. You can tell it's got a solid in there because it is blocking some of the light that's going through it. So even though there are clear spots, it still qualifies as a precipitate. All right, so we already know that sodium and anything, so inner, inner, is not going to be the precipitate. So I'm just going to get rid of those right away. Get rid of the arrow. So we have copper, which is +2, aqueous, plus hydroxide, And then it's not charge balanced, so you got to do the swap and drop, and you end up with CuOH twice is your solid that's being formed. That's the blue gel. So now we got to balance it. So we have one copper, two hydroxides. So we need a 2 in front of the hydroxide. And so that would be your balanced net ionic reaction equation for that one. And when you go to do the lab, there's about 20 reactions that you'll need to write net ionic reaction equations for. All right, so wrap up for the last lesson in Unit 3. So solubility describes how well a substance dissolved in water. And if it's soluble, it will dissolve. It stays aqueous. If it's insoluble, it does not dissolve. Double replacement reactions only occur if you form a molecular, and we didn't look at an example of that, but there is one in the lab, or something that is insoluble product, a precipitate is formed. Solubility rules can be used to predict the products and determine whether a double replacement reaction will occur at all. And then we had a definition. Spectator ions are the ones that start out aqueous and they stay that way. They do not form a precipitate. They're just watching what's going on. And then net ionic reaction equations show only the parts that are actually doing something. So we're leaving out the spectators. And that's because that's the part that actually did something interesting. So that's it for this lesson. Thanks for listening.